All right, so part three. So our next person in our story after uh, Copernicus is Tycho Brahe. So why do we care about Tycho Brahe? Well, Tycho Brahe was the nephew of a rich duke in the what is now known as Denmark, and Tycho Brahe, when he's a young man, witnesses an eclipse. Now, the thing about that eclipse that he witnesses is that, according to the Ptolemaic model at the time, that eclipse was supposed to happen a day before it happened. And according to the Copernican model, which they knew at the time, that was supposed to happen a couple of hours later. And so the problem is, the models weren't perfect. And this infuriated the young Tycho Brahe. So probably nowadays we would say that Tycho Brahe was obsessive compulsive, to be perfectly honest, had OCD. Um, uh, but Tycho Brahe makes it's his life mission in order to, because what he supposes is that he doesn't care which of the models is correct. What he says is that if they had better data upon which to apply the models, that the predictions would be better. So Tycho Brahe makes it his life mission to get better data. So what he does is he goes to his uncle, who's the Grand Duke at the time, and says, I'd like to create an observatory. So the Grand Duke gives him an island off the coast of Denmark and a bunch of people, because that's what you could do in that day and age if you were rich. And he creates an observatory. Not only does he create an observatory, but he also creates some astronomical devices. He creates these two astronomical devices. Well, actually, the devices have been created in the past. The thing on the left is known as an astrolabe. It is used for measuring angles around a sphere, because we talked about that spherical geometry from before. And this device on the right is called a sextant. And the sextant is also can be used to measure angles for locating the stars. Now, here's what Tycho Brahe did. He didn't just create an astrolabe and a sextant. The astrolabe and sextants that he created were 2 stories tall. And that meant that on the place where you put your markings for your measurements, you could be insanely precise with those angles, because if you take up your protractor and look at it, you can get down to the single angle because it's so small. But if you make that 2 stories high and a story wide, you can put a lot more divisions there. And that's what Tycho Brahe is able to do. He's able to take data to a level of precision that is 10,000 times more precise than any measurement that had been made prior in recorded human history. Now, even better than that, what Tycho Brahe does on his island is he spends 20 years every night taking data, or at least forcing his assistants to take data, right? And then recording that. Up to that point in human history, there had never been a data-taking project of that level of precision and that level of repetition to ensure that the results were precise. So not only precise in terms of the relative precision of the tool, but also of the relative precision of the data set. And Tycho Brahe develops this incredible data set that is 20 years long. Now, the thing is, Tycho Brahe himself is not a mathematician. He doesn't know what to do with it. He is just an engineer, and he dies before anyone does it. How does he die? Well, Tycho Brahe got himself in some trouble. He liked sleeping with other men's wives. He indulged in that. He got challenged to a duel. He got his nose chopped off. That's not how he died. He made a golden prosthesis for his nose. Kind of a fun fact about him. He died because his bladder popped after drinking too much. And he died in screaming agony as the poisons inside the bladder dissolved his internal organs. Or at least that's one of the going theories. Fun guy. Anyway, Tycho Brahe gives his all of his data, though, to a young protege that he takes on in about 1600, and his name was Johannes Kepler. And Kepler is a mathematician and tries to make sense of this. The thing about Kepler, though, is he thought he was going to inherit the island, but he's a commoner, so that didn't happen. So he inherits the data in 1601, but doesn't really do a lot with it for many years because he doesn't have any money. So he actually goes back to Copenhagen and he becomes an astrologer, right? Like horoscopes, swindling rich people for several years in order to make ends meet until people find out he's a fraud. And so eventually he's like, okay, maybe I'll try and do something with this data in order to make my way through. And he spends then 7 years with Brahe's data in order to figure out what's going on and eventually publishes a book. Now, because he's poor, the information doesn't really get out there, and he actually dies penniless in a gutter, to tell you the truth. It's not until well after his death that someone finds his book and they're like, oh, this is pretty good. It becomes very famous after his death. Anyway, in his book, Kepler outlines 3 laws that he was able to derive from Brahe's data, this insanely precise data set. So all of those, and we now call those 3 laws the 3 laws of planetary motion. Now, here's the thing about those laws. Those laws are what are known as empirical laws. We saw that word before when we were talking about the Renaissance, when we talked about the rise of empiricism. Empirical, E-M-P-I-R-I-C-A-L. Kepler's laws are empirical laws, meaning they're a description of what we know to be absolutely true, but they never say why they're true, right? Galileo's law of falling bodies, that was an empirical law. It said what was true, not why it was true. So Kepler has 3 laws of motion. Here's the first. It's in pictorial form. He says that the planets don't go in circles. They go in ellipses. And so here is the ellipse. We'll talk about the shape of an ellipse a little bit more. An ellipse doesn't have a center. It has what are called 2 focal points, right? The foci of the ellipse. And he says the planets all orbit in elliptical orbits with the sun at one focus. The other focus is empty. Now, this picture is a vast exaggeration. The foci are actually much closer together when we're talking about the orbits of the planets, right? And so he's able to prove that. So here's that statement that I said. Here's Kepler's first law. All planets orbit in elliptical orbits such that the sun is at one focus and the other is empty. Okay, here is a little bit about the math of an ellipse. We have the 2 focal points, right? We're going to call this point here, which is the point of closest approach to the sun, it is called the perihelion distance. Helion meaning sun, peri meaning closest, as in the word perigee, which is a point of closest approach. And this point is called the aphelion point. It's the furthest from the sun in the orbit. Helion, once again, meaning sun. Ap for apogee, which means a point of furthest recession. So perihelion, aphelion, vocabulary you want to have. But here's an ellipse. An ellipse is like a stretched out circle. So rather than having a radius, we say it has a major axis, which is the longest length across the ellipse, and a minor axis, which is the shortest length across the ellipse. And then the 2 focal points are separated by a certain distance here. So what we often talk about in mathematics is how elliptical is your ellipse? How stretched out is that circle? Well, there's a mathematical measure for how stretched out your circle is, and that is something that is called the eccentricity. And it just measures how elliptical your ellipse is. Okay, and the eccentricity is, so bring that up, it's the distance from focus to focus divided by the length of the major axis. So going back over here, it's this distance divided by this distance. Okay, so what we would see here is that the eccentricity would be 0 for a circle. The reason is because the 2 focal points overlap at the center if you shrink them down, and then you just have 1 radius. And all ellipses then have an eccentricity between 0 and 1, right? The closer you get to 1, the more stretched out the thing is, the less circular it is. The closer you get to 0, the more circular it is. Now, Kepler was able to figure out that these orbits were ellipses, but for years and years and years and years and years and years, everyone said circles. Well, why? Well, I think the fact gets revealed when you start looking at the eccentricity of a couple of the inner planets. The eccentricity of the Earth's orbit is 0.017, and for Venus it's 0.007. It's a very small eccentricity. So what does that mean? That means that the orbits are virtually circular, that there's not that much of a distinction between the ellipse that they actually are on and the circle. So how come no one saw it before? And the answer is very simple. Kepler was working with the precision of Brahe's data. Everyone else's data did not have sufficient precision in order to see this very tiny distinction. So it is the glory of Brahe's data that allows Kepler to see something that no one else was able to see. So next, Kepler's second law. If you want to watch it as an animation, I have a link there for you. Actually, why don't we just quickly go out of this and we'll do that. And what we see is our planet going around the sun. And you'll notice here what they have is, the radius of orbit. And you see the radius of orbit changes as it goes around the circle. And what ends up happening here, and we'll do this again, is they're coloring in these sections of the orbit. But if you watch this, right, what's happening there is, we can go back, is it's coloring in each of those sections in the same amount of time, okay? And so what Kepler's second law says, and I'll start this slideshow right back up, is that if the amount of time to go from A to B is equal to the amount of time to go from X to Y, then simultaneously, these two areas have to be equal to one another, right? Or if the two areas are equal, the two times have to be equal. It's called the law of equal area and equal time. And it's such a bizarre thing that Kepler thought to calculate the idea of area. The way he got the idea, or so we get from his journals, is thinking about the minute hand of a clock. If you think about it, every 15 minutes, the minute hand of a clock sweeps out the same area, 1/4 of the circle. And he wondered the same thing here. Now, these areas are devilishly hard to calculate because the numbers are so large. Remember, Kepler doesn't have a calculator. He's multiplying 14, 15-digit numbers by each other by hand. Like, you might just multiply one thing in a day, and that's your entire day. That's how long it takes. So it takes him a long time to figure out and do all this math. And he's able to figure out that these areas are equal when these times are equal. And so we get Kepler's second law, which says the radius from the sun to a planet sweeps out equal areas in equal times, right? But that's not what's important. What's important is what that means. If these two areas are equal, that means the time from A to B is equal to the time from X to Y. But notice here, A to B is a longer distance than X to Y. But these two times are equal. That must mean that the planet is moving faster here than it is there, which is the corollary to Kepler's second law, which is because the lengths of the path are unequal, as the planet is closer to the sun, its instantaneous speed is faster. So the closer it is to the sun, the faster it goes. So that means it's going fastest at the perihelion point and slowest at the aphelion point. Why is that important? Well, if you notice, Kepler's laws overthrow the Greek aesthetic, this idea of constant speeds and perfect circles. This is a departure from it. And it's only the precision of Brahe's data that allows us to move past it. So there you go. Kepler's first and second law delineate the new shape of the orbit and something that goes on with the path in terms of the different speeds. But now we need the Kepler's third law. There's not much to say about the individual orbit of any planet. So what Kepler thinks then is there's got to be a relationship that unites all of the planets together, right? Because it's a solar system. And what he figures out here, I'll go back to that slide in a second, is that Kepler's third law says that if you take the mean orbital radius cubed, right, because you can't say radius because it's ellipses, technically it's rather the mean orbital radius, that's the length of the major axis. So if you take the mean orbital radius cubed over the period squared, that number is the same for all of the planets. Okay, and let me go back to that. So that's what we have here. We have the period in Earth years, and we have the period in something called AUs. And AU is, if you notice, Earth is 1 AU of a radius. The distance between the Earth and Sun on average is the definition of an AU. So Mercury has less than an AU, Venus is less, all these more. That if you take this number squared and this number cubed, right, and you put them in a ratio, you get the same thing, okay? And here it is, what we would do, we would plot it and straighten the curve. So if I plot mean orbital radius cubed, orbital period squared, you do get a straight line, okay? All right, so that is Johannes Kepler. So empirical laws describing everything to do with the solar system. So next we go on to Galileo. Galileo, in his wrote a book. The book is called The Two New Sciences. And in that book, the two new sciences were astronomy and kinematics. We actually have already explored, because all of our kinematic equations come out of the two new sciences. We also know the law of falling bodies that comes out of the two new sciences. Two other things that Galileo did. He did the period of the simple pendulum, take a mass, put it on the end of the string, and let it go back and forth. And he figured out that you could use that apparatus in order to measure the strength of the gravitational constant at a location in space. I will show you that equation the next time we meet. And he uses that in order to verify something. He's actually finding a value of little g. So he finds little g when he does his law of falling bodies, and he verifies it using the simple pendulum. He also invents a telescope and uses that telescope to look at certain things like the moon and Jupiter. And Galileo actually gets himself in trouble with the church for the book, The Two New Sciences. And part of it has to do with, in that astronomy section, he supports the heliocentric model, the Copernican heliocentric model. And that's problematic, right? Because Galileo lived in Italy, the center of the Catholic Church's power. Also, his observations with this telescope were not good. Well, for the Catholic Church. He looked at the moon and saw it as a barren wasteland. What was the Catholic Church describing that as? A heavenly body. Well, your heavenly body is a barren wasteland. Not a good look. Other thing, Jupiter. He saw that Jupiter had 4 moons, right? Now, we actually know that Jupiter has a lot more than 4 moons, but he saw 4 moons of Jupiter. Earth only has 1. We're not that special. That enraged the Catholic Church. Or at least the Pope at the time, some cardinals at the time. Something else that Galileo does is he takes Kepler's third law, which says the ratio of r cubed to t squared is constant for all planets. And he says, well, these 4 moons of Jupiter, I wonder if Kepler's third law is valid for them. And he finds out it is, except that the value of the constant is different, right? So what Galileo does is he generalizes Kepler's third law to say Kepler's third law, r cubed t squared, is equal to a constant for any 2 objects orbiting the same mass. And we'll prove that later. So he generalizes it. But anyway, Galileo gets himself in a heap load of trouble with the Catholic Church. He's brought in and he's told he needs to recant his beliefs and write a new book presenting equal sides of the argument. Okay, equal sides of the argument. Sounds familiar to today. Is like, oh, you have to give equal time to 2 ideas, even if one of them is lunacy. Anyway, he does. So Galileo's like, fine, I'll write your book. And he writes a book that's called The Dialogues. And he has, it's a very popular structure for philosophical argument at the time. What it is a dialogue between 2 characters moderated by a third character. So the third character asks the question, and the 2 people who put the 2 ideas out there say what they want to say. Normally at the end of those sort of dialogue books, then you synthesize those together into a common understanding. Galileo promises not to do that, just to present both sides. Okay, so 2 things that Galileo do with this book that piss off the Catholic Church. One, at the time when you publish scientific works, you publish them in Latin. Not a lot of people read Latin. Anyway, Galileo published the two new sciences in Italian, and not just Italian, but the local street dialect that most people read. So he wanted this thing widely published, and he gets it published on the printing press, widely published. But the kicker is the character name for the person who represents the geocentric model. The person who puts the heliocentric model out there argues it perfectly. The person who puts the geocentric model on, he names the character Simplicio. And Simplicio, in that dialect of Italian at the time, translates as the village idiot. So, the Catholic Church is not happy. They call him back. They try him. They arrest him, and they put him on house arrest for the rest of his life. He actually dies in house arrest. Anyway, fun. If you actually go to Florence, you could actually go to the Galileo Museum. I recommend it. It's fantastic. Has a lot of equipment. This is some of Galileo's original equipment, but they've gathered scientific equipment from the time period, and I thought it was fascinating. This is actually that telescope that Galileo invented, the actual one that he used. Weird thing with Europeans, this is actually Galileo's right pointer finger. Why do they have it? But they do. There it is. Okay. Galileo, in doing the kinematics, he invents, he does stuff with ramps in order to investigate acceleration. This is a model of the actually, this is the actual ramp that Galileo invented in order to do it. He had these bells along the line. As the ball whirled down, it would ring the bell. And by spacing them at the appropriate levels, he's able to actually get the bells to ring once every second in a uniform thing, even though the ball was going greater and greater distances. It's fantastic. Oh, here's the front cover of the dialogues that I was talking about before. Fantastic. So now we jump forward to Newton, right? This link is exactly what I showed in class today with the Newton's canon. So the Principia, published in 1687, as we know, goes through the calculus, as we talked about before, goes through optics. So he invents his own telescope, the refracting telescope, to match Galileo's telescope. It's even better, more powerful than that one. And he gives us Newton's laws of motion and universal gravitation in this. Here's that law of universal gravitation we talked about. Big G, M1, M2 over R squared. We will show how this can be used in order to verify Kepler's third law in class. And then because this law matches Kepler's third law and gives the same result as Kepler's third law, we have finally the empirical Kepler's third law matches with the theoretical of Newton, reinforcing both notions. It's pretty fantastic, and we'll see how that functions. So Newton, the law of universal gravitation, so important. But like I said before in class, that Newton never knew the value of big G. So he wasn't actually able to do any of the work with the verification, because without the value of big G, you can't show anything works. And in fact, we don't know the mass of the sun, the mass of the moon, the mass of the Earth without knowing the value of big G. When we look at the satellite motion equations, we'll see how we can use the satellite motion equation to find the masses of all these objects once we know the value of big G. So how do we find the value of big G? Well, an experiment is done in 1797. That's then published and widely put out there in 1799, verified. And it's called the Cavendish experiment. You'll see Cavendish did it over the course of 2 years. Here's why, because it's such a finicky little experiment. So what he did was he took this bar, and on the end of the bars, he put two masses. They're 1 kilogram masses. Then what he did is he suspended that bar on a wire. Now, it's a very special type of wire. He actually took a piece of quartz, heated it up, and drew it out into a long, thin wire. Quartz is ductile, ability to draw it out into long, thin wires at high temperatures. The weird thing about quartz is if you take something and you twist it, right, certain things don't twist, but other things twist. A quartz wire is like a spring that it takes a very specific amount of force to twist it by specific numbers of degrees. So I can use the twisting of a quartz wire as a force meter. So he puts this bar on the end of his quartz wire. And it's called the torsion balance. Torsion is a fancy word for twisting. And then he puts two large masses over here, 10 kilogram masses, and then weights. Because what happens then is there's a gravitational attraction of this. So this gravitational attraction pulls these things closer, and that bar tilts towards the big masses. Now, here's the thing about this experiment. It tilts, and it takes a while in order to get into equilibrium because it's going to overshoot its equilibrium position and then eventually come back into place where the attraction from the masses is balanced by the quartz trying to twist it back into place. Then you measure how far it deflects, and you're able to measure the size of that force. Now, here's the thing, though. The force, as we know, between these two masses is going to be really small. That means it takes a long time for this to move into position and get into equilibrium. In fact, it takes about 12 to 14 hours in order to get into equilibrium, depending on how you set up the experiment. And anything that disturbs the experiment in this time period means you have to start over. A breath of air, a wind, disturbs the experiment. If the ground shakes, it disturbs the experiment. Cavendish eventually ends up going into the countryside to get it away because he couldn't do the experiment in London. He couldn't do the experiment in any city because the ambient shaking of everything didn't work. Mount Pinatubo, which is in the Philippines, exploded during this time period. He had to stop experimenting for a whole time period because a volcano on the other side of the planet exploded for a while. He ends up suspending the entire apparatus on a bed of mercury, mounted on a bed of springs, in a vacuum-sealed chamber, and is eventually able to take his data, and it just takes forever. I did this in college, and I had to go in to the science building on weekends because I couldn't do it during the weekday. I had to go in on Sundays when the building was shut down. No one else was in there because the elevator in the building, or people opening and closing doors, or the fact that the air system would be on weekdays and on Saturday disturbed the experiment. I would have to start over. I tried during the weekdays, it didn't work, so I had to do it on Sunday. And so I had to go in and get campus to shut down the building for a bunch of days, and I was only able to get that for certain days. I tried 9 times to take data. I got 5 data points. Now, like Cavendish, I was able to get a result that we now know is within 6% of the original answer. Obviously, people did better versions of the Cavendish experiment, got better and better and better and better values. But I was very proud of my value that was within 6% of that. But it is a terrible, finicky experiment. But that's the outline of how we got to that equation and know so much about our universe. It came from going from the Greek knowledge where we had this idea of astronomy getting tied to religion very early in it. And it took a long time to disentangle that, where we could do that work and not be blinded by certain aesthetics or paradigms that made us see things that didn't exist. That's actually really true in modern science today, is that we have these notions of what is true, that sometimes it takes anomalies, like when they finally saw that the Ptolemaic model wasn't giving the right predictions, that such that Brahe wanted to take better data, and then we found new things. That happens in science all the time. We believe something is true until phenomena occurs that make us want to think differently. Then technology enables us to get better data, and then we create models and revise models. That's why nothing is ever finished in science, because we can only say what is true now to the best knowledge of our technology's capacity, and we have to acknowledge that we're working within a paradigm, and that sometimes those paradigms or aesthetics can change. So I hope you found this interesting. There you go.